is Mike Erlihson, and I'm a head of AI in a small stealth mode company which is called Bold AI. But today I'm going to talk about something different. Today I'm going to talk about some possibly new revolution at our doorstep, and this revolution is about neural net architectures. Everyone here have heard about transformers, right? Okay, so we're going to talk about something which has some potential to replace transformers. Okay, and the plan of this lecture is to explain you some math at some extent of this new, very interesting approach. I know that this is a dev forum, and many of you as developers, and then it can be a bit hard for you. But still, I'll try to explain the main building block of these new architectures. And why do we need new architecture? Okay, this is the outline of my lecture. We'll talk about transformers and RNNs. How many of you remember what is RNN, LSTM, GRU? Oh, you are old enough. Right. And then we'll discuss the importance of memory representation in sequence modeling, because, you know, our language is a sequence. And when we talk about something which is called the Legendre memory unit, Legendre was a French mathematician, I guess, 200 years ago. And when we'll talk about some generalization of this model, which is called SSM, space-based model. And then we'll talk about some cool stuff about SSMs. Okay, some details about me. I'm quite active on the media. I have some followers on LinkedIn, and I have 2 channels on Telegram, in which I'm posting my deep learning paper reviews. I've written about 400 deep learning paper reviews, most of them in Hebrew and part of them in English. I also have the 2 podcasts and Twitter. You know, I love doing what I'm doing. Okay, let's talk about transformers. Okay, what are we doing in our LLMs? What is the basic operation we are doing in our LLMs when we're generating text? Yeah, we are predicting next token. Okay. And how do transformers predict next token? Okay, you need to build some representation of the next token, and the transformer is doing it, takes into account explicitly all the tokens from the context. And as you can understand, if this context is very long, we have a problem. Okay, but we have very big cons of this approach. And this pros of this approach, and this approach, it can be easily parallelizable and training. And why is it good? Is it good? It is good because now we are training our transformers, now LLMs, of dozens of trillions of tokens. If we can't do it in a parallelizable fashion, we just can't do it. Okay? So here we have the good and the bad about the transformers. And the good is they are parallelizable at training, and the bad that the transformers are quite slow at inference. And what about RNNs? Part of you remember what are RNNs? Where in RNNs we have a very different problem. Okay? In RNNs, the inference is very, very fast. Why the inference is very, very fast? Because while predicting the next token, we don't take into account in an explicit fashion all the tokens in our context. We build some 1 or 2 or 3 vector representation of our memory. Okay? And that's why the inference is quite fast and is quite efficient. But here we have a problem. And by the way, this is the main reason why all these RNNs, GRUs, LSTMs, why did they die? Why don't we see them now? Okay? And the main reason is that not about vanishing gradient, not about exploding gradient, not about all this stuff like this. Okay? These are problems which could be overcome But the main problem, which could not be overcome in any way, because it is at the core of this architecture, they are not parallelizable at training. We can't train RNNs in a parallel fashion. We can't predict several tokens at the same time, which we can do this transformer quite easily and quite inherently. And this is a problem, and this is what killed RNNs. Okay, so as I wrote here, RNNs and transformers, no free lunch spotted. One is fast in inference and slow in training, and the second one is vice versa. The question now is, can we build some efficient, but better than RNNs, memory representation, which doesn't require to access all our past tokens in the explicit manner, like transformers do. And here comes something very unexpected. This paper, by the way, is not very popular and didn't get enough credit. And this paper suggested to do something which can sound you very weird. Okay, as we live in a discrete space, you know, our images and our language and our videos, all of this stuff are in a discrete space. And here, this paper just proposed to put all this stuff in the continuous space. Okay, just look at it as a signal. Okay, and then if we imagine that our model past is some continuous function, some continuous signal, usually u of t, and we can think about memory as about some way of remembering this function, of representing this function in some way. And what is this way? And why does it call legender? It is called because we want to represent our memory. We want to represent the past values of our signal, of our function usual t, or u of t, as a linear combination of orthogonal legender polynomials. Okay, and m of t is just our memory representation. And we will see how we can get our token representations from this m of t. Okay, so we get our function, we get our signals, which is continuous now. Think about some continuous tokens, some audio signals, and when we just represent it as a sum of polynomials. So, and the coefficients of these polynomials is our memory. And these coefficients are actually the memory representation we need. Okay, here is the picture. We have an input signal, and here we have our representation. Here we see as far as we're close to our point t, our representation is better. And it happens also in the LLMs. You know, they are better in short context than in long context. These are legender polynomials. And now, but why is it good? Okay? How many of you remember what is the ordinary differential equation? Very simple. Oh, some of you remember it is good. Okay? Sorry. It turns out that for the legender memory unit, if you build your polynomials in a proper way, all this memory representation can be represented by a very simple differential equation. Why is it very simple? Because it is kind of linear. You know, A here is just a matrix, and M here is just a vector, and U here is just a function. So it is very simple differential equations. And this equation describes the propagation of your memory. And this is our memory representation. You know, we move one token right, we might update our representation, and this is the update. Okay? And this is all the formulas. These are not very important. And this is the scheme. Okay? And this is all the formulas. It may be a bit frightening, but you know, the most important formula is here. Okay? And this formula is a linear transition between the memory representation of this LMU or of SSM's space-state models. Now I want to ask you, why do you think, what is the real reason that RNN died? Why are we not using it? Oh, they are not scalable, but why? Why they are inherently not scalable? We have a loop, but why can't you compute it simultaneously? Actually, it's not very complicated. Here you see some linear transition between the memory, between the state t and t minus 1. Do you see here linearity? It's just multiplication of the matrix A. In the RNNs, it is not linear. In RNN, all these relationships in memory propagation are not linear. And this just ruins the parallelization. We can't parallelize stuff which is not linear. You know, all linear functions, they can compose them and still remains linear. You know, you add some tan H or sigmoid, and you can't compute it simultaneously. And this is the main reason why RNN died. Excuse me? In RNN? Yes, we can use propagation, but it is not a problem. The problem is that, unlike transformers, we can train them in a parallel fashion. We can use practically the same techniques. So, and here you see the basic unit of state space models. And here you see your signal x of t, and here you see the hidden memory representation of h of t. And here you see how we build this representation of this memory h of t, and then we build the output representation y of t. So it is very, very simple. By the way, it is not, we are not going to use it as is. We have more building blocks, but this is the main unit of the SSMs. Okay? But you know, it looks like very simple. We want to replace our transformers with this linear representation, all this sum. And the reality is quite bitter. It does not work very well. Although we can train it in parallel fashion, it is very fast in inference. We will see it in a minute. But still, it is not expressive enough. We have some problem to choose A matrices, hyperparameters. So it does not work very, very easily. Okay? And now, let's talk about the discrete domain. We like discrete data, all our data is discrete. And here we can take these equations and we can discretize it. There are many methods of discretization. I choose two of them. And here, we are starting to get equations which are very similar to RNNs. RNNs, LSTM, any of you who remembers what is RNN, or LSTM, or GRU, may recognize that it is very simple. But what is similar? What is dissimilar that the propagation between hidden states now is linear. Okay? And this is the main problem of the RNN, which actually killed them. Okay, so we gotten rid of all the non-linearities. Here is our equation of hidden state propagation. And now we can train it in a parallel fashion, just like we train our transformers. Okay, because we solved the main issue of the RNN. Okay, and if you look at it, I just drew it in several ways. It is just RNN. But why can we train all these SSMs in a parallel fashion? We can train it because now these transitions, this linear transition between memory representation, allow us to write all this stuff. Yes, do you remember when I said that composition of linear functions is linear? And this is the way we can utilize it. And this is a formula which actually means that we can train our SSMs in a parallel fashion, like transformers. And also, the inference is very, very fast. Why inference is very, very fast? Because our memory, all our memory, is compressed into one vector. Okay, just in RNNs. But now we just get rid of the nonlinearities of the RNNs. But we have a problem here. It looks like convolution, but it is very long convolution, not convolution you got used. Well, any of you who still work with convolutional neural nets, we have a convolution of length 3 or length 5. Here, we can have convolution of length 1 million, okay? Because, you know, it depends of your context length. If you want to work with context length of 1 million in a parallel fashion, you need to compute your convolution of 1 million length. And it is a problem. And it means that we can't just take any matrix A. Why can't we take any matrix A? Because we need to compute A in power of K. And raising an arbitrary matrix A in the power of K is quite problematic because it is very computationally intensive. So the most of the research of the SSMs now is concentrated on how we choose this matrix A. Okay? So now we discussed three representations. One is a continuous representation, okay, of these SSMs. The second one is a recurrent representation that was just started from. And the third one is a convolutional representation which allow us actually to train these SSMs in a parallel fashion. Okay, let's skip these slides. I don't have much time. Okay. So now we need to compute all this convolution in a efficient way. So the choice, as I already said, choice of matrix A is crucial. We can choose our matrix A as diagonal because, you know, raising diagonal matrices in the power of K is very convenient and can be computed very fast. Unfortunately, it doesn't work so good. And we have many dozens of papers which discuss how we choose matrix A, which actually works, which actually we can build a good model of it. Okay. We can quite easily build some deep architecture with the SSMs. By the way, what I described is just a building block of the SSMs. Okay? We can dress some nonlinearities which are implied on our input. Many very complex nonlinearities, we can stack them, but still we will maintain our parallelizable training because if we maintain the linear transition between the hidden states. The input, we can do whatever we want. And we can do quite complex stuff. So there are many papers which try to build deep architecture with the SSMs. Okay, but what is the problem with this very plain and simple approach? Do you remember the matrix A? And I told you that this matrix A is time invariant and then is dependent on T. It is not so good. Why it is not so good? You know, we are building our memory representation, and this representation, this matrix A or other matrices, does not depend on the input. Okay? We love our linear transition, but still this matrices doesn't depend on the input, and it can be a problem for the in-context learning side tasks. How many of you know what is in context learning? It's prompt, you can call it prompt engineering, yes. Okay, I prefer to call it in context learning. And for example, for this selecting common task, all the SSMs, before the SSMs I'm going to introduce now, miserably failed because of this fact, because we built the memory representation without good dependence on the input, also induction hand tasks. And here I want to, the last thing I want to talk about is Mamba. And Mamba is a selective SSM. And what is a selective SSM? As I already told, the main problem for the in context, in prompt engineering, in context learning size is the constant matrices of A, B, and C. And the Mamba and the authors of Mamba suggested to make it dependent on the input. Two of them, not three of them, only B and C. Okay, and this way we can at least hope to perform all these in context learning tasks in a good way. Okay, and one more point, and it's a very important point, and I don't want to skip it, is hardware optimization. The hardware optimization in SSMs is crucially important because we need all this very long convolution. Think about 1 million context. We need to compute it very efficiently. So we need to architect our architecture to support very, very fast computation. So we need this game between small and very fast GPU memory and the big but quite slow HBM memory of the GPUs. And the last thing Mamba suggested, by the way, Mamba is a very seminal paper. When I told you that the gender memory unit didn't get credit it deserved, this paper got a lot of credit and it deserved it. And the last thing they suggested to use this called gated MLP or multi-layer perceptron, and at least according to the paper, it really helped to improve the performance. So, what did we learn till now? We have transformers, which are fast in training and slow inference, RNNs, which are slow in training but fast in inference, and we have Mamba, which are fast in training and also fast in inference. Okay, so life is good, right? But maybe there is some problem here. Life can't be too sweet. Okay. We just replaced some nonlinear propagation of the memory by some linear propagation. And usually when we replace some linear stuff, with some nonlinear stuff, but linear stuff, something bad happens. And something bad which happens is that our expressiveness is going down. So our model it's at least theoretically, is less capable of expressing some tasks, maybe complex, maybe not complex. And this is one of the problems of the SSMs, because SSMs didn't replace our beloved LLMs. By the way, we are a very interesting blog of very interesting model, which is called Jamba by A21 Labs, which suggested to use SSM layers together with the transformer layers. But still, we have this expressiveness, I say bottleneck in the SSMs. They are still not expressive enough, but we can use them for data with a very, very long context. And why can we use it for data for the very, very long context? Because if you have a context of 1 million, maybe many of your tokens in which concepts in this context are not so important. Okay? And this in these scenarios we can use our SSMs. I need 1 minute, okay? 1 minute. I know that our time is over, I need 1 minute. In the scenarios which we need to get some information from our very low context, but most of the part of our context are not so relevant. In this case, we can use SSMs. And when it happens, it may happen in our audio processing, it happens in the genomics, it may happen in video processing. Till now, I didn't see a lot of usage of SSMs for video processing, but still I hope it will happen. There are some papers which claim that it can be used to some small and efficient LLMs. Maybe it can, but I guess LLMs not gonna be very good. And it is the end. I just go over this slide, and you need to remember that is very active. SSMs are very active area of research. I took one of the repo, and here you can see it's a very small portion of the papers I saw in this repo. Hundreds of papers only in the last year, only about SSMs, Mamba, Mamba 2, Mamba 3, Mamba for video, Mamba for audio, Mamba for genomics. The field is exploding, at least academically. Till now, you don't see too much models which are SSMs based. By the way, there are one more models in addition to Jamba, which are mentioned, which just combined transformers blocks and SSMs, which are, I remember one more paper which combined it in a different fashion. But still, I think the future is, we have some revolution at our doorsteps, as I mentioned in the title of my lecture, but SSMs are not going to replace transformers. But we need to learn how we use SSMs together with transformers. Maybe we can replace many of our transformers layers by SSMs, because there are many papers which state that many layers in the transformers are redundant, we can get rid of it. Maybe instead of getting rid of them, we can use SSMs instead. So the future is in combining. Now I'm done. Thank you very much.